investing an hour in today's topic, which is to look at how to incorporate probabilistic forecasting into optimization solvers like FICO Xpress. And this is really a getting started talk. So for folks that have perhaps incorporated forecasting and optimization before in the past, but have done so via point forecasts, and looking to transition into, what is probabilistic forecasting all about, and how can we accommodate those into linear, mixed integer linear, and so on, different solvers in FICO Xpress. This really is the getting started talk for how to do that. So let's go and jump into it. Before we get into the probabilistic forecasting framework so far, I want to address why not point forecasts. And the reality is, in any supply chain, type of decision or industry you're in, it could be energy, banking, finance, manufacturing, transportation, logistics. Decision makers know that uncertainty is present in their decisions. Uncertainty, call it volatility, what have you. And so if we go back to them with one optimal solution from one point forecast, that's going to elicit a bit of skepticism from them in terms of moving forward with that 1 point forecast decision. There's a great quote by Thomas Sowell where he says, "There are no solutions, only trade-offs." And so I invite you to think about, as we move forward through this presentation, to think about not solutions, but in terms of trade-offs that we're going to be talking about when it comes to cost and risk for how we assess the solutions coming out of these models. And then last but not least, risk and uncertainty live in the tails of the distribution. And not only do point forecasts ignore these entirely, but they provide mean and or median estimates that are about as far away from those tails as possible. And so think about, as we go forward, how do we accommodate risk and uncertainty via the tails of these forecasting distributions, and how do we accommodate those into optimization models? So if not point forecasts, then what? The first approach we'll talk about from an optimization standpoint today are going to be called chance constraints. And what these do is that they make decisions that meet demand some user-defined percentage of the time across all the plausible forecast scenarios that PyMC is going to generate for us. And what this focuses on is on the frequency of those demand shortfalls. And so the question on the third bullet point focuses really on what this type of methodology answers for us, or what type of question this methodology answers for us. And that's based on all plausible future demand scenarios. How often am I willing to allow production to fall short of demand? And we can choose whatever user-defined percentile from that forecasting distribution to help accommodate and insert that into an optimization model. The other approach we're going to talk about today is, we'll see it later defined as CVaR, or conditional value at risk. And this focuses not so much on the frequency, but on the severity of the losses in the most extreme but plausible scenarios. So this is arguably a bit more of a conservative approach when we talk about risk. We want to be extra risk sensitive, but that can also come with a trade-off of increasing cost, right? So if we want to buy certainty, that may cost us a little bit more. And so it's those inherent trade-offs that we're going to be working through in the example later today. The question that this approach asks is, based on all plausible future demand scenarios, if production falls short of demand, how severe am I willing for those shortfalls to be? And so frequency and severity are going to be the two terms we focus on, with the two different kind of getting started approaches for incorporating probabilistic forecasting into optimization modeling. Again, kind of summarizing those two here, both of the techniques we're going to talk about today are going to use first the probabilistic forecasting distributions across all plausible future outcomes generated for us by PyMC. And so the example, just kind of a very simple getting started example. We have just a univariate time series here of daily electricity demand in Ontario, Canada. And for the time series practitioners out there, we can take this univariate series, we can do our favorite time series decomposition. We can look at the autocorrelation function plot, the partial autocorrelation function plot, evaluate whether or not there's a unit root present, decomposed by trend, seasonality, and to try and get a good idea of what is the systematic variation that is in this time series. Because the goal is we need to take this one univariate time series and forecast daily for the next 6 months what we project energy demand to be in Ontario, again, daily for the next 6 months, which is going to be about 180 different forecasts into the future that we will need to make. But the forecast itself doesn't make a decision. The forecast itself helps provide context and input into what's generally a much broader type of optimization or decision intelligence problem. And the very simple example we're going to use today is just a very simple power generation problem, just to kind of convey the concepts and the differences between chance constrained and CVaR. So you'll see the business objective is to determine how much electricity to generate for each power source each day over the next 181-day planning horizon. You'll see 5 energy sources: nuclear, hydro, gas, wind, and solar. And you'll see various different inputs or parameters that we'll use in the optimization model for each. You'll see the available gigawatts or gigawatt hours per day for each source, which effectively will serve as an upper bound for daily supply each day for each source. There's a cost, or rather a marginal cost, for how much it costs to produce one more megawatt hour of each source. And last but not least is kind of an indicator indicating whether or not each source of energy is clean. And so pretty much all but gas is considered clean. Down below, you'll see us introduce just a simple constraint into both of the optimization models that at least 80% of total electricity generation each day must come from clean sources. So give you guys a second to take that in. We've got to do some forecasting, and then we also need to take the output from PyMC and embed that into a much broader decision or optimization model. For the forecasting part, let me turn it over to Daniel Saunders, our Bayesian PyMC expert, who will walk us through that approach in PyMC.
Thank you so much, Jay. So as I'm Daniel Saunders, I'm a data scientist with PyMC Labs, which is a consulting company that focuses on Bayesian models. And kind of my section I want to tell you about is the kind of how do you build the forecast, what are your options here, what are the tools available. So it'll focus a little bit on a model for estimating energy demand in Ontario, and then focus a little bit on the software stack that I think is a powerful and interesting option you might want to explore in your own work. So there's lots of forecasting methods out there. If you use many of the off-the-shelf available ones, you'll get a single prediction, a point estimate for every day in the future. And maybe you pick a model that looks something like this. We can move to the next slide. This forecast is going to be insufficient for a few kinds of cases that you might have. Suppose, for example, that your goal is to meet demand 99.8% of the time. The point estimate I've showed you is the kind of expected value of demand over the next bit of the future. But the expected demand and meeting demand 99.8% of the time are pretty different sorts of problems. If you meet expected demand, you're going to kind of roughly serve demand half the days in the future and miss on the other half, which is inadequate. Many provinces and states have standards about how often a blackout is allowed to occur, and it might be a rule like 1 blackout in 1,000 days, which means that energy planners really care about tail risk, and they don't particularly care about expected value of demand. The other case where this is point forecast can be insufficient is whenever there's an asymmetry in the kind of costs and benefits of meeting demand. So underproducing electricity is quite bad. You have to shut down factories or hospitals, or people can't run the refrigerators. Overproducing electricity is kind of bad because it's expensive and maybe wastes precious resources. But they're not the same kinds of bad, and that you want some kind of function that can trade off these two things. And once you're doing that, you're no longer in the regime where you can just reason about the expected value. We can move to the next slide. What Bayesian methods do instead is they'll give you a full probability distribution for each day in the future. So this is the Bayesian version of the model I was just showing you. And it has a couple of simple components. It has a kind of general default demand, some kind of intercept. Then it has two seasonal components. There's a bi-yearly seasonality to it, where we expect demand to be higher in July and December when people need a lot of climate control, and much lower in the spring and fall. And then there's a weekly periodic component as well. Maybe demand spikes on Fridays, but then tapers off on the weekend because people stay up later on Fridays, but don't go to work or school on the weekend. So when you have this distribution, there's a lot of nice things that you can do with it. We can move to the next slide. You can ask questions like, what's the probability that demand is 500,000 megawatt hours or more? Which is a really important question if you're planning for the future, because you need to know kind of what will be sort of peak capacity, what kind of surge capacity do I need to plan for? And you can see on the y-axis there that the very top of this plot cuts a little bit over 500,000 megawatts per hour for future demand. You can also do things like, given any proposed energy generation plan, you can quantify how good or bad will that be over the range of plausible futures. And that can give you distributions of other quantities you're interested in, like a loss distribution, for example. And that will be kind of really relevant for us when we start talking about CVaR. We can move to the next slide. So that's the kind of intuition for what kind of forecasting model you might want to build and why it's useful. I want to talk a bit more about the tool behind it. There's a software package called PyMC. It stands for Python Monte Carlo. It's an open source package that's been in development since 2005 and is quite mature and powerful at this point. We can move to the next slide. If you haven't run into Bayesian methods much before, I want to give you just a very surface level explanation about what it's about. You might have a vector of parameters that we'll call theta, and these are the parameters you're interested in learning. What's unique about Bayesian methods is that you don't start off by assuming that it could be any value. You put distributions on each one of your parameters kind of before you look at the data. These distributions are called prior distributions, and they're meant to represent things like your background beliefs about what you know about the problem that aren't driven by the data, or things like regularization. In frequentist statistics, there's this regularization concept that says we got to pull parameters towards some kind of neutral point, typically 0. It introduces a little bit of bias, but it can reduce overall variance and it can reduce overall expected error in the long term. And priors are one way of encapsulating that. Bayesian inference is a way of going from one distribution to a new distribution, where that new distribution has been updated and informed by the data. And the update rule is described here on the screen. You have your prior on theta, your vector of parameters, and then you multiply it by the ratio of how well does any particular parameter explain the data versus the average parameter in the set. That's kind of what the denominator represents, is the expected probability of the data kind of averaging over all of the parameters you might have. And in the end, you get a posterior distribution. You get posterior distributions for every parameter in the model, but you also get a posterior distribution for all predictions that the model makes. And that's what I was showing you a couple screens previously. If frequentist statistics is your practice, I'll just make a little pitch for why you should consider something else, and that's that Bayes' theorem is a universal estimator. Given a data and some model, you can get a posterior distribution, and you can estimate parameters that you're interested in. And that's really powerful because it cuts out a whole kind of range of tricky problems. In frequentist statistics, you get a whole zoo of different estimators. You know, this estimator is good for this kind of model with this kind of data in this situation, and that trades off bias and variance in this way. And you have to pick between the huge range of estimators to get the one that's appropriate for your problem. With Bayesian inference, all of your questions about what's appropriate for my data and what kind of regularization do I want are just encoded into either the likelihood, the prior, or the model structure. So I think it keeps things conceptually clean to organize things that way. But that's enough of my sales pitch for Bayesian statistics. I'll talk a bit more about the mechanics on the next slide. So PyMC, because it's trying to give you this universal estimator feel, it wants to be very open-ended in what it can do. And it has a building block style API where you essentially just write down mathematics, and it will build you a algorithm that can estimate the posterior that you're interested in. So here, I've truncated the model. It's a bit bigger than this, but you have some mean prediction, which is a function of some intercept, those periodic functions that we talked about earlier, and then maybe also a trend, something like Ontario's population is growing or shrinking, so we want to estimate the kind of overall trend. One unique feature is that we have prior distributions in the modeling language, which is, we can move actually 2 slides forward. Yeah, I want to focus on this middle line here. We have prior distributions in the modeling language, so you can say this parameter is distributed by an exponential distribution, and with some shape parameter that I want to control. So sigma represents a parameter related to the noise around the data. And I can just say, I expect sigma to be small, or I expect sigma to be big, or whatever kind of rule that I want to apply to the prior distribution. You can move to the last part, which is the likelihood. The likelihood is the kind of last interesting choice you get to make. What this says here is that given some expected value, which comes from my intercept, seasonal, and trend components, I'm going to have some distribution of errors in the data around my prediction. Maybe I'm far away, or maybe I'm close to the right number. And I can describe how I expect that distribution to be shaped via this likelihood assumption. And in this case, we picked a log normal. A log normal is a nice distribution for being asymmetrical and heavy-tailed on the right side of the distribution. And that is useful in power demand because when things go as expected, you'll predict the right value. And when things go unexpected, it's rare that it's like really good for you. Some unexpected event happens in the world, and suddenly people need way less power. Not as common as the other way around, where there's a heat wave and you need way more power, or there's some kind of natural disaster and you need more power. So we should expect that errors should be asymmetrically distributed around their expected value. And extreme events should be kind of described and captured by the likelihood. So that's the model in a nutshell. We kept it really simple. We can move to the next slide. I want to talk a little bit about how these machines work. So the idea behind PyMC is that we want to be able to, I'll back up. Many machine learning frameworks and frequentist estimators use kind of optimization as the tool for your estimator. Bayesian statistics tends not to do that so much. We tend to be more interested in sampling from a probability distribution. You have this posterior you're trying to get to, and there's a number of ways to describe it. You can describe it analytically, you can describe it with an approximating distribution, or you can describe it with samples. And samples is kind of the leading story in our world at the moment. And there are powerful algorithms that can generate samples from arbitrary probability distributions where we don't know exactly what your distribution will look like, but we can figure it out as we go. And one of the main tools here is known as the Monte Carlo Markov chains, which will find a location in a distribution and then propose a jump to a new location and accept that jump with some probability. And you can construct them very carefully such that when you jump around the distribution, you're jumping exactly the way a random number generator would. The kind of state-of-the-art technique is known as Hamiltonian Monte Carlo, where you create a little physics simulation and you roll a particle around in this two-dimensional Gaussian that I have depicted here. You roll it for a few seconds, you stop it, you change its direction, you roll it around, and you stop it again. And if you do that enough times, you'll collect accurate samples from the distribution. We'll move to the next slide. I just want to give you 2 more details about PyMC before handing it back to the optimization side of this talk. This one is about the software architecture. PyMC is built on this very neat tool known as PyTensor, which is a symbolic computation library, which handles things like automatic differentiation, but also it can construct a compute graph of your model, a kind of string of symbols and connections between them, and then analyze that graph to look for things like, oh, this sequence of operations, it can actually be replaced with this other operation that's numerically identical, but more numerically stable or quicker. And it really helps with our theory that we're trying to let modelers just think about the model. They just think about priors and likelihoods, and they don't have to think about numerics, because we will build you a cleaner version of your model and a custom sampling algorithm behind the scenes. And once we do that, we can write machine code to various levels that work on different kinds of computers. So we can work through JAX to get you to GPU optimized code, or we can work through Numba to get you CPU optimized code, or C, depending on your installation environment, roughly. The final slide in my section is just that I want to let you know that if you get building a Bayesian model and you get stuck, help is available. PyMC Labs is a separate organization from PyMC, but it has a collection of expertise in how to build these sorts of models and can help you resolve your problems. And we create a number of tools specialized for marketing, causal inference, and agentic Bayesian inference as well, which I'll let you explore on your own, but I'll give the time back to Jay.
Awesome. Thanks, Daniel. So back to kind of the simple power generation example that we were walking through connecting PyMC and Express. Since PyMC is primarily a Python package, we're going to leverage the FICO Xpress Python API so that these 2 things play well together in a much broader decision workflow. And so if you are unfamiliar with the FICO Xpress Python API, you just come in and import it just as you would your other favorite Python packages, NumPy, Pandas. You'll import PyMC as well. But we also have other APIs into really pick your programming language of choice into C, C++, Java, so on and so forth. I'll let you guys take a look at the slide there. I think you'd be hard pressed to find a language that FICO Xpress doesn't support in terms of getting your models into that language and then later into a production environment. In this webinar, we're talking about like one very small slice of FICO Xpress technology. We're talking about the FICO Xpress Python API, and then the solver component are the various optimization solvers available at our disposal to use to solve any formulation of this problem. You'll see that later on, the 2 examples, the chance constrained and the CVaR model, we're using a simple linear programming solver to solve these. Of course, they get much more complex. And easily inside of FICO Xpress, we can extend that to mixed integer programming. If we have quadratic objectives or quadratic constraints, we can choose the appropriate solver from there. So we'll have really any solver option we need inside of FICO Xpress to solve these problems. We also have Insight, Workbench, Moselle, and Compute Interface. And for sake of time, I'll let you guys read these on the screen, but Insight is essentially our interactive visualization environment for displaying results and for various types of scenario testing. Workbench is our IDE for the environment where you build the model. Moselle is our algebraic modeling and programming language for introducing your sets and your parameters, decision variables, and crafting your objective constraints, and then eventually solving that model. Again, you can also do it through the Python and so on, different APIs, but Moselle is another option available to you. Then last but not least, the compute interface for integrating FICO Xpress capabilities into custom applications for enterprise-wide adoption. So let's start with the first chance constrained model. And what you'll see highlighted specifically is where do those scenarios generated by PyMC fit into this specific model. So you'll see the sets. We'll have three different sets. First is just going to be a set of all of the 5 different power generation sources. We'll have a set called C, which is just a subset of only the clean power generation sources. But notice T will have one set of days in the planning horizon. So I believe it was 181 days it is that we're forecasting ahead. In the parameters, you'll see different parameters corresponding to the various columns that you saw above. 80% for that clean energy target, which we're denoting theta in the model. But down below, this is where those scenarios are being incorporated from PyMC directly into the FICO Xpress model. Notice D sub T beta. These are a user-defined percentile of demand each day. So recall PyMC generated for us 4,000 samples or 4,000 probable scenarios each day. And so in this example, we're just choosing the 95th percent or the 95th percentile for each day in that 181-day planning horizon. So what D sub T beta is going to give us is effectively just a 181 by 1 vector of those 95th percentile estimates that we can read in to the chance constrained model. We have one set of decision variables, X sub ST, which is the electricity generated by each source on each day for that entire 181-day planning horizon. The objective function is just to minimize total cost across all sources and all time periods. Where those PyMC scenarios in the chance constraint model get incorporated into the model themselves is in this demand satisfaction constraint, where we're saying that the total amount supplied must be greater than or equal to those 95th percentile values for each day in that planning horizon. And I'll draw your attention to the 2 lines of Python code down below for just showing how easy it is to get to extract those 95th percentile demand values from the output of PyMC and read those into the constraint inside of Python. Last but not least, this has less to do with the Python or the PyMC example, and more is just including that clean energy constraint to ensure that at least 80% of the total power generation each day comes from clean energy sources. And so you can see the kind of software agnostic formulation above, along with how to program and implement that explicitly inside of the FICO Xpress API. When we run this, the chance constrained model will minimize total cost while satisfying demand in approximately 95% of those forecasted scenarios each day. And again, we just arbitrarily chose 95% for every single day. It's user defined and at the discretion of the modeler what that value is to choose, and should it be consistent across the entire planning horizon, or should you choose 90 for one day, 95 for another. that's completely open and to your discretion. But one thing I'll point you to is notice, there are a few scenarios across these 181 days where we miss. And I'm kind of pointing to one here. You can see a few where the actual demand exceeded the supply. And notice that the chance constrained model does not control for the severity of those misses. And that's, as we transition to the CVaR model, the CVaR model explicitly focuses on controlling for the severity of the kind of worst case scenarios. So this CVaR model in FICO Xpress, it's not inherent to FICO Xpress. In fact, this is the Rockefeller-Urashev model that we're going to use, which is just a linear programming model that we're building inside of FICO Xpress. It's just an extension of the chance constrained model that you've already seen. And so what I'm going to put down below on the screen are only the additions to this model. And in fact, Daniel and I and a few other colleagues at FICO, Bruno Vieira, and one of Daniel's colleagues, Evan Wimpy, we wrote a blog in more detail. I believe it's in the chat. If you guys want to drill down into the specifics of each model type and really dive into the details, that blog is available and should be linked in the chat for you to take a look at. But the big difference here is in the chance constrained model, we essentially just read in a vector of percentiles. Whereas in the CVaR model, we're reading in every single demand scenario generated by PyMC. So just doing the math, 4,000 posterior samples over 181 days is going to be over 700,000 different scenarios that we're reading in to PyMC, and we're calling that set omega. Because this number, as you can see, can get quite large quite fast. In practice, and again, it's up to the discretion of the researcher or modeler, but that omega set could include a representative sample of demand scenarios as well. And you'll see, again, highlighted in yellow is the parameter for where we're incorporating those PyMC demand scenarios. So D sub omega T, again, for each scenario, for each time point. So we're going to read in all 780 some or 724,000 different parameters into the model. And this replaces D sub T beta from the chance constrained model earlier. Remember, chance constrained, that D sub T beta was just 181 by one vector. This is now for every scenario across all time points. So we're jumping from 181 to approximately 724,000 parameters that we're now reading in. A few other parameters that this conditional value risk model provides is a parameter called P, which is the user-defined penalty cost, in this case per megawatt hour of unmet demand. And this is user-defined. Typically, we set P to a value larger than the highest marginal cost for the source. And the reason we do that is to make unmet demand more expensive than meeting demand with the most expensive currently available source. But again, ultimately what P is user-defined. Alpha is the tail probability of the shortage loss distribution that's used to calculate CVaR. And this will make a little bit more sense as we go forward and introduce the objective and constraint. But in this example, we're going to set it just to 0.05. But what that means is that the CVaR term is measuring the average shortest cost across the most extreme 5% of scenarios in that shortage loss distribution. And then lambda is the weight placed on the CVaR risk in the objective function. And I think this will make more sense once we see the objective function, because the objective function is going to have two objectives. And we'll go ahead and jump in and take a look at that momentarily. For the decision variables, we're going to have a shortage decision variable, again, for each scenario, for each time point. So 724, was it? 1,000 decision variables that we're adding to this model. And this is going to define for us the unmet electricity demand in each scenario for each day. Down below Z is our value at risk threshold. And what this does is this is one point along that distribution that separates what we deem to be ordinary shortage cost outcomes from the most extreme. And so the most extreme are going to be what penalizes, is what's penalized in the objective function. And Z helps us determine what that cutoff is. And last but not least, there's an auxiliary decision variable for each scenario, which quantifies the amount of shortage cost in each scenario that exceeds that VAR threshold Z. And so again, there's a lot more kind of intuition unpacked in the blog that talks about how and why these things work together if you're new to the CVaR model. So I encourage you guys to take a look at that if you're interested in potentially using this. But down below, you can see in Python how to easily declare these decision variables using the Python Express API. I told you about lambda in the objective function, and you'll notice in the objective function, we're essentially just extending what was originally in that chance constrained objective. So in the chance constrained model, we are just there to minimize cost. And you'll see that component is in the CVaR model as well. But the extension for the CVaR model is now we're introducing a CVaR risk penalty defined here. So we're starting with the value at risk level Z, and we're adding that alpha fraction of values that exceed or the most extreme values that exceed that VAR threshold Z. That lambda term is a penalization. And so in a sense, this is a multi-objective model with two competing objectives in this one objective function. If we want to buy risk and if we are much more risk averse, that's likely to increase cost. If we're a little bit less risk averse, we can oftentimes get a lower cost. And so typically when we run the CVaR model, we're not going to run it once. We're going to iterate through that value of lambda to look at the various trade-offs on an efficient or a Pareto frontier for what is that CVaR risk and total cost trade-off to look at multiple solutions on that two-dimensional axis. Down below, the shortage constraint replaces the demand satisfaction constraint from the previous model, and it defines shortage as the amount of demand that exceeds planned generation. So if demand exceeds supply for a particular scenario on a particular time point, then shortage is going to be a positive value greater than 0. But notice if supply is greater than demand, because we set a lower bound earlier for that to be greater than or equal to 0, that was what Rockefeller and Urship did to linearize this model, as opposed to taking the max of either 0 or the difference between demand and supply in this case. So we expect shortage to be 0 inflated, but 0 inflated to what point? Ultimately, we'll have to take a look at that in the results from the model. But it's this shortage variable that's used to construct that shortage loss distribution. Once we have that shortage loss distribution, it's then the alpha fraction of those tail scenarios that are then penalized in the objective function. And I see a lot of folks on the call, some of whom I know are experts in the energy sector. And but both of these model formulations are linear programs, and they were purposefully simplified to show the mechanics of how each one of these models works. But in practice, things are far from simple. These models can also include binary unit commitment decisions, startup and shutdown costs, ramping limits, reserve requirements, certain minimum up and down times. And so the problems can get much more complex. And I don't want to pretend that these two models we've shown today are you know, production ready by any means. These are more of just kind of getting started with the basics of chance constraint and CVaR, and then adding that complexity along the way as the real world interferes. Regardless of which solver you need to solve these, though, FICO Xpress contains, again, a suite of linear programming solvers, mixed integer, quadratic programming, quadratic constrained quadratic programming, mixed integer quadratic programming, and so on and so forth to help accommodate a lot of these different types of additional factors that need to be accommodated in your model. Let's take a look very quickly at the results for when and how we ran these. And there's a link that should be in the chat to a GitHub page where you can take all the code that was written and run and replicate these yourself. You can run and replicate them. You can choose different values for lambda and choose different values for that P parameter. You can choose a different clean energy constraint if you want to, and look at these and kind of learn by doing. But the results that we ran is that the CVaR model recommends generating about 8.5% more electricity on average per day, increasing the total cost by about 22%. So the CVaR model is more risk averse in this particular case. You can take a look at the two examples on the right hand side. In the chance constrained model, on average, we were expected to generate about 460 gigawatt hours per day. With the CVaR model, to help cover those extreme alpha tail cases, that number was instead 500 gigawatt hours per day. But that comes with a cost, right? That's a little bit more expensive relative to the chance constrained model, which was just looking at those 95% percentiles. And then you can see from a shortage risk perspective, chance constrained was at 5%, whereas CVaR dropped down to 0.35%. And so effectively, if we want to buy more certainty, that's going to come at a cost. And so again, going back to that trade-off between risk and cost, especially for the CVaR model, we can run and toggle that lambda parameter. In this case, we did it from 1 to 1,000 and looked at different solutions along a Pareto frontier. And so you'll see on the y-axis is the generation cost, which was the first part of that CVaR objective, along with the shortage rate, which was created from the second part of that objective with the CVaR risk penalty. And now this gives us a much clearer pattern and a much clearer picture to help make reliable and robust decisions under uncertainty. You'll notice the red Pareto frontier looks at it with an 80% clean energy policy. And we went back and said, okay, well, what if that number were to be changed from 80% to 90%? How does that Pareto frontier differ? And so we did that. We went back, kept everything the exact same, changed to 90%, and we were able to take a look at what that Pareto frontier looked like as well. So it gave us not one solution, but many trade-offs in order for us to try to make the best decisions possible. There are some additional resources, and I've alluded to these earlier in the talk. We have access to a full blog which goes into these modeling methodologies in a lot more detail. So if you saw these and you're interested in kind of learning more about them and how to run them in PyMC and FICO Xpress, I encourage you to take a look at that full blog. If you want to run and take exactly what you've seen today and run in Python using PyMC and FICO Xpress and replicate the results that you saw, here's a link to the GitHub page. If you're curious about getting started with FICO Xpress, you just want to take a look at some more examples and get more of a comprehensive idea of what types of problems can be solved using FICO Xpress inside of the Python API. There's a separate GitHub link there for you to take a look at. If you just want to learn more about PyMC Labs, take a look at their website. I am continuing to be educated about Bayesian statistics through Daniel and many of his colleagues. And then, of course, the FICO Xpress website here for those that may be new and want to take a look at the types of offerings that Express has. Last but not least, if you want to take a look at specific Bayesian applications in Python, here's a link to take a look at many more Bayesian applications using PyMC outside of just probabilistic forecasting. And last but not least, our licensing page for if you're an academic and want to take a look at our academic license or our community license or a trial license, you can find all the information at that link below. We're getting close to the end. The last slide are just kind of final thoughts about going through this process. Express and PyMC integrate seamlessly for enterprise scale production workflows to help really make reliable, trustworthy, and robust decisions under uncertainty. In short, if I could wrap up, if I could, in one sentence, summarize this talk, PyMC quantifies that uncertainty and FICO Xpress optimizes under it. Third bullet point, it says that using point estimates in an optimization model, it ignores the risk, right? These are mean forecasts or these are median forecasts. And I think I alluded to this earlier, but its recommendations will most likely be met with skepticism by the decision makers. And with all of these problems that we build as data and decision scientists, the one question I know many of us are always asking ourselves is late at night when we're on a walk, when we're in the shower, is thinking about our model, and if this optimization model is going to fail in production, how is it going to fail? And then doing everything we can to try to mitigate edge cases and risks for making sure that once it's deployed to production, it's a smooth and seamless process. One of those answers, one of the many answers, almost always lies in failing to accommodate for that uncertainty that's inherent to the forecasting process itself. And so for folks that are interested in this or looking to transition from forecasting with point estimates into probabilistic forecasting, I strongly recommend taking a look at PyMC and then taking a look at how those results from PyMC seamlessly integrate into FICO Xpress.